If we have a set of linear equations that we've turned into a matrix equation, so A here is a matrix which encompasses all the coefficients in our linear equations. So if we have A times X, this system of unknowns, equal to a column vector B, then we can use the inverse matrix of A, and our solution X is just the inverse matrix of A multiplied by our column vector B. However, it's not always the case that we can find the inverse matrix A. It may not exist, or it may be very difficult to compute. So another method of working out the solutions in X is to use elementary row operations. So the first stage is to create the augmented matrix. So the augmented matrix is a matrix which we make out of A and B. So effectively we make a larger matrix than A by adding in that column vector B. So this matrix here will look like the matrix elements in A. That's 1, 2, and 1, 3, all the way up to A1, and this one here will be N, and A2, 1, A2, 2, etc. And all the way down to the final one, which will be AM1, AM2, all the way across to AMN. So that's our matrix A, and this is now augmented with the elements of B, B1, B2, all the way down to Bm. And we effectively think of this now as a single matrix. What we're going to do is various things to our rows. And there's only certain things we're allowed to do to these rows, and those things are the following. So we could swap two rows around. Okay, so this row could just move to where this row is, and we just swap the two rows. That's one thing we can do. The other thing we could do is multiply a row by a constant, a scalar. So the whole of row 2 could be multiplied by 2, for instance. And exactly the same as when we swap two rows, when we do something to a row, we do it to the whole row, including the B value. So when we swap row 1 and M, the B value swaps as well. And when we multiply a row by a scalar, it's the whole row, including B. The final thing we can do is add a multiple of one row to another. In fact, to a multiple of another row. Okay, so what do we do here? Let's say we're looking at row 2. What I'm going to do is, let's say for row 2, I'm going to replace the whole of row 2 by, I don't know, row 2 plus twice row M, for instance. Okay, so these are the kind of things I can do. I can swap rows, I can multiply whole rows, I can do a multiple of one row added to or subtracted from a multiple of another, and then replace that row. Why would I want to do that? Well, there's again a system for what I'm going to do. So I'll do that over here. The first thing I'm going to do is I'm going to make sure A11 here, this element here, is not 0. If A11 is 0, then swap rows. Okay, so swap the first row with another row which doesn't have 0 as the first element. So I swap whichever row I want, it doesn't really matter. I've just got to make sure A11 is not 0. The second thing I do, use these row operations, so these are called elementary row operations. Use these row operations, and we usually use the terminology EROs for elementary row operations. Use EROs to make all elements underneath that very first A11 to make them 0. Okay, how am I going to do that? What I'm going to do is take multiples of, let's say, the first row. So if A21 was 2 and A11 was 1, I could take off 2 times this row and I get this to be 0. Remember, I've got to do the same thing for every element in that row. So I get this whole row and I take off whatever I need to take off, subtract to get that, just that term there to be 0. I then look at the next one down, do the same, etc. And so all of these then are 0. So in the end, after these first 2 steps, I'll have a non-zero A11, and then everyone down here will be 0. At that point, I then forget about row 1 and column 1, and instead now look at this submatrix in here, this submatrix here. I'm going to repeat exactly the same thing for this submatrix. So the third step is repeat for the submatrix. So this smaller matrix here, forgetting about this column and the row here, I'm going to make sure this A22 is not 0. That's the first step. And then I'm going to make sure all the things underneath it are 0 by doing some elementary row operations. And then when I'm finished with that matrix, I'm going to look at the next submatrix inside that, do exactly the same thing. I keep going, I cascade down until I've finished. So I repeat and repeat and repeat until what I get is a matrix that looks like this. It has some diagonal elements, but then it's got zeros all the way down here. With my various different B values on this side. The key thing here is that this part A here, this matrix A, it used to be A, is now an upper triangle matrix. There are 0 elements in everywhere except for this upper triangle. Okay, so what do I do now? Well, now I think back to where I came from. I remember that actually this is a set of equations. The very last line here says that this value here, let's call it y, and the value I end up with at the bottom here, let's call that z. This line here, if I were to go back to this set of equations I came from, what this line is saying is that y multiplied by xn equals z. Okay, so what that says is that hopefully I can work out xn. I've simplified all of these equations now so that at least one of them is very simple. Okay, there are a number of possibilities now that we have this equation y times xn equals z. The first possibility is if y doesn't equal 0. As long as y doesn't equal 0, then what can I do? I could divide both sides by y and get the value of xn. So I get the value of xn. It's just z over y. And what I do then is, that's the solution of xn. I then look to the equation slightly above. This will be an equation which has xn and then the one before it, the other known value. So I use this in what's called back substitution. I substitute that value into that next but one equation there, that second from the bottom equation, and I will be able to get the next x value. I do the same in the next equation and the next, and go all the way up to the top, and in the end I get all values x1, x2, x3, all the way up to xn. Okay, that's only possible if I can divide by y. That means y can't be 0. The next possibility is if y equals 0, but z doesn't equal 0. Okay, what happens there? Well, what I get is 0 times some unknown quantity here. Still, 0 times anything is 0. So I get 0 equals z. But z isn't 0. So this is a contradiction. That means there's no solution. In the first case, I can find a solution. In fact, it's a unique solution, just one solution. In this second case, when y is 0 and z isn't 0, there's no solution at all. The final case, when y equals 0 and z equals 0, what does this last equation tell me? It tells me 0 equals 0. Nothing wrong with that at all, except for the fact I can't find the value xn. So in fact, xn is any value. So what we do is we say, well, we'll set xn equal to some unknown. Often we call it the Greek letter lambda. So this is just an unknown value. And then I'm going to use back substitution to find all the other values. So then use back substitution. Okay, so a rather complicated method. It is a very long-winded method using these elementary row operations, getting into this upper triangular form, and then often doing this back substitution to find the solution.